right? So it means you take water vapor, pass it through a boiler. After a boiler, you go to a turbine. After a turbine, you go to a condenser. From the condenser, you come back to a pump, and then you're back here, right? So this is obviously a turbine. This is condenser. This is a pump. And this is a boiler. So what are the important things about this? So it's a cycle that has four components, right? What's the role of a turbine? The role of a turbine is to
Generate work power.
generate work, and the symbol that we use for this is W dot T, right? What's the role of the pump? It's to pump the water, right, from the condenser back to, and this one uses work, right? So we typically input work into this, and we call this WP. What's the role of the boiler? To add heat to the system, right? So we call this Q in, and the role of the condenser is to Q out. Okay. Okay. So the cycle is going in a clockwise direction, right? What's another important thing about this cycle? What's this state in here? The numbers, right?
1.
Okay, always 1 is the entrance to the boiler, to the turbine, and then 2 here, and then 3 there, and then 4 here. Okay, and we are going kind of in this fashion. Now, if we take a look at this, and then, again, without looking at the book or anything like this, right? We're just looking at this. You should be able to draw this without any problem, right? Now, if I look at the turbine produces work, right? What do you think is this work equal to without looking at your book? Just by
M dot times H1 minus H2.
Thank you. Yeah. So the work per unit mass, right, is equal to H1 minus H2. Why? It's because, you know, the enthalpy here is higher than the enthalpy there. And if I go in that, you know, in a clockwise direction, and I would say Q out divided by M dot, what would that be equal to? H3 minus H2 or H2 minus H2? I mean, these are absolute values, okay? So it's H2 minus H3. How about WP divided by M?
That's
H4 minus H3, yes. And lastly, Q in divided by M dot is H1 minus H4. See, that was really nice and quick, not a problem, right? And what is the efficiency of this cycle equal to? Let's say in terms of the W's, what is the efficiency equal to? If you were to just say, without again looking at the book, say, I'm just going to find out what an expression for the efficiency is, okay?
Q in over W cycle, right? W
The
cycle
out-
over Q in.
It's W cycle, it's output divided by input, right? So it's W, but what kind of W? I have 2 W's in here. Well, it's W cycle, you're right. Divided by Q in, right? But W cycle is equal to what?
W T over M minus W.
Okay, so the net work that you're getting is really WT minus WP. See, this one I'm paying, I'm not getting, right? So the equation then becomes, what is WT? It's really H1 H2 because the M dot cancels out, right? Minus WP, which is H4 minus H3 divided by Qn, which is H1 minus H4. You see, all those equations that may have looked complex, really, if you draw the cycle and then just use a little bit of common sense, you could actually reproduce all those without any problem. Okay? Because also the efficiency can be written as what? Instead of the W cycle, you could write it as, do you agree that you could write it as Q cycle divided by Q in? Why did I write that? Because remember, for a cycle, the Q's are always equal to the W's, right? So, but then Q has two things. You know, it's got one Q that goes in, the other Q that goes out. So the Q net is really the Q in minus the Q out divided by Q in. So in terms of the H's, because at the end of the day, really, when you analyze a cycle like this, how many properties do you have to evaluate? 4. H1, H2, H3, H4, okay? Once you get those, you can answer all these questions without any problem. So Qn is obviously what? H1 minus H4 minus Q out, which is H2 minus H3 divided by Q in, which is H1 minus H4. There is also another quantity that we have learned about, which is called the BWR. Anyone reminds me what that is?
Backward ratio.
Backward ratio. Yes. Backward ratio. What does it represent?
It's work the turbine over the pump. Other way.
It's okay. It's
Pump
the work
over
of the
turbine.
pump divided by the work of the turbine, and you want this to be as small as possible. Okay. So again, according to these equations, right? What would that be equal to? WP would be H4 minus H3 divided by WT, which is H1 minus H2. See, you can answer so many questions by doing that. Now, in addition to drawing a physical cycle like this, what do we typically do? We also typically draw along it what kind of diagram? Temperature versus S. Okay. Why is it temperature versus S? Is because we have constant pressure, two constant pressure processes and two isentropic processes, right? So if you have this versus S, and remember what we typically have is a dome like this, and we operate between how many pressures? Two pressures. You have the high and the low, right? So the high pressure is somewhere here. The low pressure is somewhere there, right? So where is my state number, what does my state number one cycle start? For a Rankine cycle, it starts right here, right? And then how do we move? We move isentropically, that means constant entropy, right? Down like this, to state number 2. Right? So what am I going through here? I'm going through the
Oh, sorry, you're going through
1 to 2.
Goes to the
the,
turbine.
yeah.
Through the turbine, right? So my pressure goes down, my temperature goes down isentropically, right? Then between 2 and 3, what am I going through? I'm going through the condenser. The condenser just at constant pressure removes all the extra heat. See, I want to turn all my vapor to just liquid, right? So my state number 3 is going to be here. Then Then between 3 and 4, I'm going through the pump, right? And the pump just increases my pressure. How? Isentropically, that means I have to move up, right? Until I hit what? Until I hit the high pressure, right? And we call this point 4, right? And then between 4 and 1, what's happening? You are going through the boiler, right? So here you have compressed liquid, so you keep adding heat, now the liquid, until the liquid becomes saturated liquid, right? As you keep adding heat, obviously the temperature does not change because you have a change in phase, okay? So this is the good old Rankine cycle. Ideal. Okay? Between when you go from here to here, we talked about an approximation for how you calculate the work produced by or consumed by the pump or used up by the pump, right? What is that work was equal to? What is the approximation? WP was equal to, I think we said V3 times P4 minus P3. Did I ring the bell a little bit? Wait, I'm sure I have shown it somewhere. But where is that really coming from? If you remember that work is equal to PDV, right? In other words, it's almost like work is equal to PDV. So if you have PV, let's see.
Is that P4 minus P3?
P4 minus P3, yes. Yeah.
Is that an equal sign? Work P.
That's approximately. Approximately. Why? Because between here and here, the V is there, but here it gets more compressed. Technically it's less, but really it's liquid. So we just use the value of P4 at V3 and then just multiply it by the pressure difference. And then you go, why is because, it's too mathematical, I'm not gonna do derivation. Well, I was gonna do the derivation of it, but then I say, what's the use, right? It involves some differential calculus. It's not even done in the book, but that's fine. Then what we started talking about afterwards is, what are the problems with this type of cycle? As the fluid goes from 1 to 2, that means you're going through the turbine, you got a lot of vapor in it, right? Water particles that are there, which come in at very high velocity, they impact the blades, and then they erode the blades, okay? What's the first solution that we obtained, that we know about to increase to alleviate this problem?
Reheater?
The superheat is the first one, right? What does the superheat do? What is the idea behind the superheat? Well, the idea behind the superheat is that, hey, why am I starting directly here at the superheat, at the saturated vapor, right? Because if I start from the superheated region, good. If I start from the superheated region here, and then I come down, what benefits do I get?
Higher P value.
I have a higher
Well,
X value here,
Yeah.
a higher quality, that means less particles. But then there is another fringe benefit in there, which is high efficiency. Why do we get higher efficiency? Because the temperature of heat addition now has just been pushed up, right? And remember from the Carnot efficiency, which is 1 minus Tc over Th, as Th goes up, you get better efficiency. So you got superheat, two benefits, right? Okay, which are high X and high efficiency. What's the other one?
When you have that, isn't there less corrosion? You mentioned that last time,
Yes,
because of the higher quality.
higher quality, yeah. But there, we have another amendment or improvement from this ideal cycle to the reheat, right? What does the reheat do? Well, the reheat, I hate to erase this, you guys cannot see. Well, in the reheat, what you're doing is you're coming like this, right? To some intermediate pressure, right? And then what do you do? You reheat, right? And then you fall again like this, right? So you come in like this, go like that, and then come in like this. And the purpose of the reheat is to, really the main purpose is to increase the quality, okay? Now, this part that we just talked about here is really the key part of chapter 8 that you should really be familiar with, okay? Now, the rest of the stuff that we're gonna talk about, I'm not gonna neglect it, right? Some further improvements in the stuff is just to kind of understand, you know, what other things can be done to this, but all the other stuff is not gonna be in exams, okay? So this is what you're expected to know, at least for this chapter. Obviously, for the previous chapter, you had the, how do you calculate the exergy if you know what the dead state is, you know, how to evaluate the change in exergy. So if you've done some simple, other homework problems, you should have absolutely no issue.
So even the superheat and reheat cycles, we should be able to solve.
Well, the superheat will always be there, because in some states you're told that you're starting from superheat.
Oh, okay.
So you don't always start from there. You may start from there,
Okay.
just so you know. It could be directly from here, if you're told you're starting from a saturated vapor, right? Or it could be you're starting from there, but not in all those cases you have 4 states that you need to evaluate.
Okay.
The problem with the other states is that it's not like they are complicated. It just adds more state that you have to evaluate, you know, and the more states you have to evaluate, the more possibilities for messing up, right? Okay, so let me get my little thing. So at least to get us back to where we stopped last time, and then we'll pick it up from there. Okay. So let's see if we get me to that spot. So we talked about the engineering context. We talked about, you know, where does the vapor power, you know, kind of fit in the overall vapor power plant. You know, it's just a sub-part really of the vapor power plant. And then it talks about the different components, the 4 different components: boiler, turbine, this and that. And then we talked about these equations. Now you know how to get them without, hopefully, even remembering those, right? Just by looking at this. The key prerequisite is to really draw this one correctly. And then once you get those 4 states, then you can calculate, obviously, the efficiency. using either the work information or the heat information, just like we did in here, work information or the heat information, which turns out everything is a function of H's. And then we also talked about the back work ratio. The back work ratio, which is the ratio of the work pump to the turbine pump, and obviously you want that to be as small as possible, and in terms of the H's, this is what it is. And then we said that if we assume here that you have no heat loss, that the process is reversible there and reversible here, meaning you don't have any heat losses and you don't have any, sorry, never mind. If you assume that the flow here through this piping is occurring at constant pressure, which in real life it doesn't do, right? But if we assume that you have, it's like an ideal fluid, there's no friction over the surface, that means that the pressure remains constant. And likewise here, when it flows over the condenser, if you neglect pressure losses, that means the pressure is constant. Here we are assuming that you have no losses through the shell of the turbine, nor the shell of the pump, and that it is reversible, okay? Then if that is the case, if you have no heat loss and it's reversible, that means it's isentropic. That's what isentropic means. That means that in a TS diagram, you're going to have two constant pressures and then two constant entropy. Then we talked about this, and this is that approximation that I was mentioning before, the integral of VdP, right? Which is approximately, you usually just take the V3 here and then just multiply by the pressure difference to get what the work is. We talked about the four processes. Two of them are constant, two of them are isentropic, two of them are constant pressure. And then we look at this problem very carefully. You should be able to reproduce this without any problem, you know? So you draw the physical system, you know, you draw this thing, and then from there you should be able to answer all the questions. And then we moved up, and then we said that whenever you increase the high temperature, remember, why is that? Because if you recall, eta Carnot is 1 minus Tc over Th, right? That's kind of the general rule. If you increase Th, efficiency goes up. If you decrease Tc, the efficiency goes up. So either one. If you do both of them, you're lucky, you know, then you can get even better. So graphically, we just shown how that's done. There's no need to go back to those. And then, another quantity that is of interest in here, and this equation kind of looks complex, but really it's yet another equation that you could probably figure out without even doing this. What is the isentropic efficiency of the turbine mean, right? In this thing, we are saying that the entropy is constant as you go from 1 to 2. That means as you go from H1 here, H2 will be H2S, because you are assuming that you are isentropic. But in reality, really, you're not moving as H1 to H2 like this, you're moving in at an angle, right? Because it's, you know, because it is not isentropic, what's going to happen to the efficiency, to the entropy? You're going to produce some entropy because of irreversibility. So really the H2 is going to be there instead of having H2S, okay? Now, if this is 2S, and this is 2, and then you go like, well, I know that efficiency is always less than 1, okay? Now, let's take a look at this. Isn't it true that where would you produce work better? Is it if the fluid is going through it isentropically or non-isentropically? Well, if you go from 1 to 2 isentropically, right, which one? I mean, what would you get the highest work? Is it when the fluid is going isentropically, or where there is some losses?
Losses.
It's when you have some losses, right? When you have some losses, if I'm starting from something here, and I wanna, harvest some maximum of work in here, what I wanna do is I wanna have less go through here. Is it a little bit complex, maybe? Okay. Well, let's look at the equation here, where it says it's WT, okay, divided by WT.
Making your H2 smaller.
Right. Okay. In other words, it's going to be, you're starting from H1 for both of them, right? Right? And we know that the work is H1 minus H2. H1 minus H2. But which one is higher? Is it H2 or H2S?
S is a little higher.
It's H2S is a little higher? Okay. So WT over M, when it's isentropic, right? You're going to have H1 minus H2. In other words, you're going to have more work, right? When it's isentropic, right? You're going to have more of this when you don't have any losses. So it has to be in the denominator, H1 minus H2S. When you do the work, the isentropic thing of the pump, then again, it's the same thing. It's WP divided by WP, but now it's the reverse. It's WP this. Why is that, I think?
Because you're putting more in versus.
Because now, if this one has irreversibility, I have to put in more work, because I have to combat, that, this efficiency H4 minus H3. When I have irreversibilities, obviously the H4 minus H3 will be higher, because I not only have to cause that delta H, but I have to fight that irreversibility that is inside. Okay? So again, I try to kind of stay away from this, and what I typically tell the students all the time, because they always get confused about this. This is H1 minus H2, H1 minus H2S. This is in the event, you have an isentropic efficiency that is less than 100%. These equations are only there to be able to calculate H2, because H2S you can get just assuming isentropic. And if this is given, then you can get H2. The rest of the analysis is exactly the same. Okay? So it's just another step in the usual calculation. So, and why are we going from 1 to 2? Because an irreversible process will be always accompanied with an increase in entropy per Newton, but not per Newtons, per the second law of thermodynamics. Okay, so, and then this example was repeated exactly the same way as the previous example, just but adding this part where you have to use the isentropic efficiency. Then we moved on to improving the performance of our cycle. We talked about the superheat and the reheat, and we talked about the problem of the ideal Rankine cycle is that it's ideal, but it causes high lower values of the quality, which could be detrimental to the function of the turbine, and therefore we want to do it such that the quality is always higher than 0.9 if possible. And the two modifications, the first one is the superheat that we just talked about, in which you are starting from here and then coming down right there. And the two benefits that you get is that you have higher thermal efficiency because higher temperature addition, and you also have a higher quality, which is exactly what you want. Another way to, and by the way, when you hear you have a steam generator. Steam generator means you have a boiler and a superheater. So if you have a problem in which it says you have a steam generator, that means you're more likely than not starting from the superheated region. Okay, keep that in mind. And then the other one was the reheat that we just talked about. In the reheat, obviously, you do the same thing. You have now a steam generator. That means you're starting from a superheated region. And you come in, you go to the turbine, as you can see, in one. But then instead of expanding in one stage from high pressure to low pressure, you're expanding in 2 stages. If you had 3 turbines, you would be doing it in 3 stages, okay? So, because you have 2, that means you have to have an intermediate pressure somewhere, which is right here. So you expand isentropically through the first one, and then what do you do with that fluid that's coming out? You pass it through the heater. That means you heat it up again at constant pressure. Then you expand it through the second turbine. Now, what's the benefit? It's obviously you're getting a better quality, right? And the other benefit that you are getting also is because the average temperature of heat addition is a bit higher, you're getting a little bit of better efficiency. The only downside about this, that's why I don't give them in exams, but I'm sure you're going to have them maybe in homework, is how many states do you have to evaluate in here? It's 6 states. May not sound like a lot, but it's 50% more than, you don't want to compare it to 4, right? So it's 6 states that you have to do to figure out everything else. Now this is not too bad, but there are others that are even worse. And then we talked about one example in which you have a reheat. Okay, I'll let you go through that one. The analysis is fairly straightforward. It's just that 6 states instead of 4. Now, improving performance, there is now another one which is called the regenerative vapor power cycle. Now, another commonly used method for increasing thermal efficiency is regenerative feed water heating, or simply regeneration. I mean, so far we've been talking about average temperature of heat addition that is kind of going up and this and that, right? But just by looking at the side of the turbine, right? Now, if you look at this in here, it's cycle 1, 2, 3, 4, 1, 2, 3, 4, A1. The working fluid would enter the boiler where, you think? Do you agree that it enters the boiler at 4? Right? And between 4 and 1, at least between 4 and A, what state is the water in there? It's compressed liquid, right? We usually call it, liquid, but it's compressed liquid nonetheless. It is as compressed liquid until you get to state 4, where it becomes kind of liquid, right? Or saturated liquid, if you will. And then compressed and be heated while in the liquid phase to state A, okay? So in all this. So this is where the regenerative vapor power cycle comes into the play. With the regenerative vapor or feed water heating, the working fluid would enter the boiler at a state between 4 and A. So they want to change this. Instead of entering at 4, you want to enter the boiler somewhere in between. And then you go like, okay, what's the deal? If you do between that, what would happen to the average temperature of heat addition? Well, let's say I'm entering the boiler here instead of here. My average temperature of heat addition would be somewhat higher, right? Because it's the average between this and 1, let's say 1 prime, instead of between 4 and 1 prime, okay? So theoretically, the efficiency would go up. As a result, the average temperature of heat addition would be increased, thereby tending to increase the thermal efficiency. So it's all nicely said and everything, but the problem is the implementation. You know, you just want to increase this, but how are you going to make it happen? Well, it can be done 2 ways. Regeneration can be accomplished using what we call an open feed water heater. That means you gotta get some hot fluid here, some cold fluid there, and let it mix before getting pumped, right? Or it could be, it says here, a direct contact type heat exchanger in which streams at different temperatures mix to form a stream at its intermediate temperature. Let's take a look at one of them. If you were just to look at this, would it make sense to you, just at first glance? Maybe you have to think about it a little bit, right? Well, let's think about it a little bit. So what is this? This is the steam generator. That means I'm starting my state one where? Superheated, okay? So this corresponds to this without any problem. Remember what's happening here, we're adding the heat, right? Then I come back in here and I see what? How many stages? 2 stages, okay? That means my mass flow rate is coming in like this, right? And it expands through the first turbine to where do you expand? Do you expand to the lowest pressure or an intermediate pressure? Better be an intermediate because we haven't finished our expansion. So we come in between 1 and state 2, okay? Between 1 and state 2, what did I do? I came down isentropically to the intermediate pressure. Now, when you do this, at 2, you're taking a fraction y of that vapor. Let's say you have 10 kilograms per second, let's say. Maybe you're pulling 3 kilograms per second that you route this way, and the rest, which is 7 kilograms per second, continues on, okay? So what do you do with the one that you pull out? You bring it towards an open feed water heater. You're gonna figure out later why, okay? So this is the hot stuff that's coming to it, okay? Remember, our goal here is to start with a kind of higher temperature of our fluid, right? So you cannot just condense and pump. If you condense and pump, this is where you're gonna end up with, right? But if I'm condensing some kind of warmer water, I mean something that is already at a little bit higher temperature, then maybe I'm gonna be somewhere there. I mean, that's the idea. So the 2 comes out, right? And goes to the open water heater, so let's forget about it for now, because I'm here at the intermediate temperature, intermediate pressure, and then the rest of it, right? What happens to the rest of it? The rest of it goes and expands to state number 3, which is to the lowest pressure. Now between 3 and 4, what happens? This is a condenser, right? So I'm going 3 to 4, I'm taking all the vapor out. Then I come back, what do I hit here? I hit one pump. I hit one pump because, you see, this vapor that I brought out is at what pressure? It's at the intermediate pressure, right? But this one that's coming through here is at the lowest pressure. But I want to mix them, so I need to pressurize the lowest one to bring it in line with this, okay? So I do a single compression here, or pump, between 4 and 5, you see here, 4 and 5, I'm only compressing where? To the intermediate pressure, right? Now both fluids meet there, they do their own thing, right? You got a cold fluid, you got a high fluid, hot fluid. So what comes out of 6? You get saturated liquid, right? If you do those fractions properly, you're gonna get saturated liquid where? At the intermediate pressure. See the nice thing about this? Instead of just going from 4 and now we just go to A and then do the rest, now by doing this operation, the mixing in here, the open feed water heater allowed me to get this compressed liquid to state number 6. Now in 6, what am I doing? I'm still at the intermediate pressure, but I need to get to the highest pressure. I do my second stage pumping, right? And I pump it between 6 and 7. Between 6 and 7, I'm just getting to the higher temperature. Now, look at this drawing in here. What is the average temperature of heat addition occurring? What is the entrance to the steam generator? Is it state number 7, right? So 7, see the average temperature through here versus A through here. Which one is better? It's obviously 7 to the thing, and therefore you get more efficiency. So, but in the process, how many states do I have now? Yeah, it's 7 states, you know, that you have to worry about. It's almost double the normal thing. Plus, you have to be careful here because mass conservation has into to play. You know, if you got fraction y here, the fraction 1 minus y there, and then you do all the rest. Can I erase this, by the way?
Yeah.
It's all good. It's really too hot in here. Is it good?
It's a little warm.
Yeah, it's a little warm.
Like 60.
So,
It just feels like.
so how would you like to analyze something like this? Would you? Would you like one like this? All right. So the heat addition here obviously would take place from state 7 to state 1 rather than state A to state 1, as would be the case without regeneration. Accordingly, the amount of energy that must be supplied. Again, you see the other stuff is that, hey, you know, you're heating up from a higher temperature than instead of starting from A. That means you're not going to use as much fossil fuel, right? It's easier to heat water from, let's say, 60 degrees to 100 degrees rather than from 20 degrees to 100 degrees, right? So anything that you get, and here what you're using some stuff that you're coming from here. The only problem is, though, the only downside, it's not the entire mass flow rate that's generating WT. You know, so, you know, some fraction of it has been taken out. So, yeah, you know, there is there's always a price to pay somewhere. Okay, so, but at least my goal at this point is for you to look at something like this and go like, I think I know what it does. Okay, if you can trace it, that in conjunction with the TS diagram next to it, you can recognize that this is a regenerative vapor power cycle, and then be able to kind of explain what it does. You know, it does this, it does that, it mixes, and it does this. Now, there are some equations on the thing in here. For example, it says that y, what is that fraction equal to? Remember, everything is a function of those h's anyway. It says y is equal to h6 minus h5 divided by h2 minus h5. And then you have another equation that says wt over m dot 1 is equal to h1 minus h2 plus 1 minus hy h2 minus h3, and then another equation is wp divided by m dot 1 is equal to h7 minus h6 plus 1 minus y h5 minus h4. Now these equations are ready for you to be used, you know, if you have homework, let's say, that's associated with that. But then again, why is it, at least for the first one, why is y equal to h6 minus h5 divided by that? When you look at what's happening in the first turbine, isn't it true that m dot 1, right, is equal to what? Well, it's equal to m dot 2 plus m dot 3. Right? Because, you know, whatever is coming whatever is coming to here is m dot 1, right? What's coming out of here is m dot 2, what's coming out of there is m dot 3. But if y is the fraction, by definition, m dot 2 is equal to y times m dot 1, because that's the fraction, right? And m dot 3 is equal to 1 minus y times m dot 1. So, now when you look at the energies, for example, right? If you look at then at the two-stage turbines now, right? How much enthalpy is coming into the system? Isn't it true that it's m dot 1 times what h? h1, right? Is that correct? Because that's h1 here. And then how much is going through the first one here? You got m dot 2, which is what? M dot 2 times h2, that's leaving the system, right? And then here you have m dot 3 times h3.
M dot 3 is just M dot 1 minus M dot 2, right?
Yes. Another, in fact, if we do the feed water, I think that's probably what it's better to do it like this. See the open feed water heater. How much energy is coming in from here? That's m dot 2 times h2, right? How much is coming out of this pump in here? M dot, how much? Because what comes in through here is m dot 3, right? M dot 3, m dot 3, m dot 3, right? Times h5. And how much is leaving? Isn't it true now?
It's just gonna be M dot.
The entire m dot times h6, okay? So if I do this, then isn't it true that this has to equal this plus that? Okay, so m dot h6 is equal to what? M dot 2, which is, we said is y times m dot, right? Times h2 plus m dot 3, which is 1 minus y m dot times h5. Now I can get rid of the m dots, simplifies, right? And then I get h6 is equal to y h2 plus h5, right? Minus y h5. And then if I factor out the 5 or the y, I get y times h2 minus h5 plus h5 is equal to h6. Then I bring the h5 on the other side. h6 minus h5 is equal to y times h2 minus h5. And therefore y is equal to h6 minus h5 divided by h2 minus h5. Which is exactly the same as this equation right here. Okay? That's just a side thing, you know, just to show kind of where that equation comes from, right? So it's not like I'm not going to say, oh, it's just an equation that's given. There is is a source to it. It's based on energy conservation through the open feed water heater, okay? I'm not gonna derive this or this, but I can just show you how it looks like. Look at how this WT over M equal to, right? Isn't it true that it's H1 minus H2? First of all, that's how much you're getting through the first stage turbine, right? It changes from H1 to H2, and then, but now it's only a fraction that goes from where to where? From H2 to H3. From H2 to H3, it's not the entire thing, it's only that fraction. I think just looking at the equation, looking at the drawing there, it makes a lot of sense, okay? And for the pump, it's the same thing, right? The work used up by the pump is, because you got two pumps now, okay? This one uses the entire flow rate, do you agree? So it's going to be, what is that? H7 minus H6. How about this one? It's H5 minus H4, but it only but only 1 minus Y times the mass flow rate that's going through it. That's why plus 1 minus 5 times H5 minus H4. Okay, enough said about this open feed water heater. Okay, now if there is an open, so these are the equations, we just talked about them a moment ago. And then the energy added by heat transfer, then obviously in this case the energy added by heat transfer Qin is where? It's H1 minus H7, okay? And then the energy out is 1 minus Y, H3 minus H4. Why is that? Because the condenser is here, and only 1 minus Y fraction of the mass flow rate is going through it, so it's going to be 1 minus Y times H3 minus H4. Again, just by looking at this, you can actually rewrite those equations directly. Okay, I'm not even gonna go through this exercise, and I don't think you should either. Well, maybe you should, just as a practice. Now, if there is an open feed water heater, right, that means there has to be a closed one, right? In the open one, the two fluids, the hot fluid and the cold fluid mix directly. They mix in a chamber, which we call an open feed water heater. But in this case, you have a closed one. Now, closed heaters are shell and tube recuperators. Shell and tube is, we're going to be studying this in the heat transfer class next term. That's one type of heat exchanger, right, in which you have one type of fluid flowing in a, it could be tubes or it could be in a pipe, and then you have another one that's enclosing it, which contains the other fluid. So the bottom line for those types of heat exchangers is that the fluids are never mixed. They are separated by a solid boundary, okay? But heat transfer will always occur anyways. So closed heaters are shell and tube recuperators in which feed water temperature increases as the extracted steam condenses on the outside of the tube carrying the feed water. And again, the key thing in here, because they are closed, the two streams do not mix, and because they do not mix, they can be at different pressures, as opposed to before, we had to use an extra pump, to pump my fluid from the lowest pressure to the intermediate pressure. Now, how does that work? Well, the diagrams below show two different schemes for removing the condensate from the closed feed water heater. So what you have is essentially you have cold water that's flowing through a pipe. You take that extracted steam, right? That extracted steam hits the walls of the pipe. What's going to happen to it? It's going to have condensation, right? So you're going to have the feed water comes in, the feed water goes out. Obviously, the feed water that's going out is going to, ideally, right? You're coming in with a low temperature, you're going to get to the higher temperature because that's really what you want, right? But in the process, obviously, what you're going to have is some condensate, right? Because the hot things, will become condensated, and then you collect it at the bottom. And then there are two ways you can do that. You can either take this and then pump it to the higher pressure, because here you're working with the intermediate pressure or the lower pressure, or you can just set up a steam trap and then feed it to the low pressure heater or condenser, either way. But the bottom part is exactly the same. The thing that you remember here is that the two fluids do not mix, and you are doing it in that fashion. Now, again, I'm not gonna spend too much time on this. This is the same thing as before. You have a steam generator starting from state number 1. You're going through the first stage expansion. You extract some steam, right? Why? But instead of having an open feed water heater, right? Where do you route it through? You route it through this heat exchanger, right? This heat exchanger is getting this cold fluid going this way, but in the process it gets what? It gets heated up, you know? You're going from 5 to 6, see? 5 to 6 at constant pressure, you have this extra temperature, because otherwise we would have just ended up here, right? And then temperature of heat addition would be this, but because we added that heat, now my average of temperature heat addition is through here. That means I have extra efficiency or higher efficiency. Again, when you look at this, you can also determine in here, using what we just did in here, that the fraction is H6 minus H5, H2 minus H7. Looking at this problem, how many states do we have in here? Now we're getting to about 8 states, okay? So it becomes kind of more complex to analyze the problem. Now, you could also have, this is just for fun, I'm just showing you this picture. Some people are crazy, you know,
Stage turbine.
under the thermal efficiency in the hope of doing that. How many expansions you have in here? See? It's nuts, right? You got 3 stages here, another 3 stages there, you know, multiple closed water heaters, and so that's not our thing, right? And the only reason in here, because some people go, if you can increase it with 1, can you increase it with more? Yeah, of course you can, but now you have got to weigh the economics of the whole situation, right? You can't go crazy. It says the thermal efficiency of a regenerative cycle can be increased by incorporating several fed water heaters at suitably chosen pressures. The number of heaters used is based on economic consideration, because at some point you say it's not worth it. Right? And getting on now to section 5, a couple of things. We talked about water as being the working fluid in the vast majority of vapor power systems, and that's what we will be using. Why is it? Because it is plentiful, it's low cost, non-toxic, it is chemically stable, and relatively non-corrosive. Another good thing about water is that it has a large change in specific enthalpy. Remember, everything here, of course I erased the darn thing, you know, WT is a function of the change in enthalpy between the 2 states. So water has the ability to have kind of high values, which is really what you want. When it vaporizes at ordinary steam generated pressure, which tends to limit the mass flow rate for a desired power plant output, because the WT is equal to m dot times H this minus H that, right? The H is across. So if you are using a suitable fluid that has large delta H, you don't have to use as large m dot, you know, to create a certain amount of work, right? As opposed to if you are having a fluid that has low delta H, you would have to use a large mass flow rate to compensate for that. When using water, the back work ratio achieved are quite low, right? And the techniques of superheat, reheat, and regeneration can be effective for increasing power plant efficiencies. Now, although water has some shortcomings as a working fluid, no other single working fluid has been found that is more satisfactory. That's what's being used. Still, vapor power cycles intended for special uses may employ working fluids that are better matched to the applications at hand than water. Now here we're not talking about really industrial uses or something like that. Let's say you can have cycles that operate at relatively low pressures, which may perform best with a refrigerant such as ammonia as the working fluid, but you're not getting the greater amount of work that you would expect. There is a word that just I included this just in case you run into it, binary vapor cycle. What does it mean? Well, in a binary vapor cycle, you have two working fluids that are used, you know, because remember, you have a boiler, turbine, then you have the condenser. The condenser removes heat, right? So what some people do, you know, in thinking of exergy, instead of just throwing that to the atmosphere, they could use that work or that heat that you are throwing out as maybe the heat into another cycle. You may not get a lot of things, but you can get something out of it. So, for example, in here, what do we have? We have two ideal Rankine cycles are combined with a heat rejection from the high temperature cycle. Topping cycle is used as the energy input for the low temperature cycle. So this is where the stuff is happening, see? This is the high temperature one, you know, you come in and the heat exchange into one, right? Instead of throwing it away, you are using it as input to the other one. What else can we say? Cogeneration, and this is just some technical words. Cogeneration is sometimes you are not just generating power, right? Maybe you want to generate power on one hand, but you want maybe steam for something else, okay? So instead of, so what you are doing is extracting some steam, and on one hand you are generating the power, on the other hand you are rewriting the steam somewhere else for some other process. So direct combustion, heating, and the generation process steam together account for a substantial portion of the industrial energy used, but because the heat and steam are often required at relatively low temperature, good use is not made of the relatively high temperature products of combustion obtained by burning fuel. This source of, because what happens with all those products, you're just throwing them outside, right? This source of inefficiency can be reduced with a cogeneration arrangement in which fuel is consumed to produce both electricity and steam, but with a total cost then that would be required to produce them individually. Again, just an example of cogeneration. Obviously, you've got your QN, your turbine, right? And again, here you're coming in and generating this, going to condenser, but here you're producing that system, or at least a fraction of that steam that you direct towards a system that requires process steam, for example. That's why cogeneration generated at the same time. Exergy accounting, I usually kind of omit this one, but let's just say a word about it. The discussions, the book has many examples at the end, but the discussions to this point show that a useful picture of power plant performance can be obtained with the conservation of mass, conservation of energy principles. That's what we've been using. We've been using conservation of energy all along, but any time we had a bifurcation that extracted a mass, you know, we used the conservation of mass, saying m.1 equals m.2 plus m.3. Now, however, these principles provide only the quantities of energy transferred to and from the plant and do not consider the utility of the different types of energy transfer. Because the moment you start talking about exergy, remember what exergy is really the economic value of energy. Now, there is no equation that goes along in here. You almost like have to do an exergy accounting in order to figure this out. So in this section, we account for the exergy entering the power plant with the fuel. Obviously what happens is a portion of the fuel exergy is ultimately returned to the plant surrounding as the network. I mean, the efficiency of those darn things are like 35%, 40%, if any, for vapor power cycles are not very efficient. I mean, you're burning, fossil fuels, you're generating really high temperatures, but really when you think about it, the amount of work that you are getting, you got, what the heck did the other energy go to, Just a lot of losses. The largest part is either destroyed by irreversibilities within the various plant components. It's not like just going out to the outside. There are irreversibilities in the system, or carried from the plant by the cooling water, stacked gases, and unavoidable heat transfers within the surroundings. So there is a lot of inefficiencies. These considerations are illustrated by 3 solved problems treating respectively the boiler, the turbine, pump, and condenser for a simple vapor power plant. Again, a quick view into this. If you look at what enters, obviously here is the fuel and the air. You have a combustion unit, right? Hot combustion products, right, through a heat exchanger, come in and heat up the high pressure water, right, turning it into from a liquid to vapor, right? But you do have combustion products that exit the thing. This is going to be at high temperature compared to, what is the dead state in here, you think? It's just the temperature of the atmosphere and the pressure of the atmosphere, right? Now what's coming out is you have high gases that are coming in, before they mix or they dissipate in the atmosphere. Obviously there's going to be some exergy that's associated with that, right? And obviously the cooling water in, the cooling water out, obviously you're taking some stuff out in here, plus some inefficiencies that are associated with pump, etc. So it says vapor power plant exergy. These are just some typical values, right? Output, the net power out is about 30%. Okay? The losses in the condenser about 1%, stacked gas is about 1%, exergy destruction in the boiler, that's where the stuff, because this is a totally irreversible process, right? So 30%, heat exchanger unit about 30%, turbine about 5%, condenser about 3%, kind of gives you an idea of a power plant schematic for the exergy analysis study. And each one of them would have, I think you get about 3 examples, right? 7, 8, and 9, and each one of them kind of goes through the different processes, right? Let's see what that is. Okay, let's take a look at this one because I think we do have a little bit of time. We're just going to look at one of them. Vapor cycle exergy analysis heat exchanger unit. Okay, so the heat exchanger unit at the boiler has a stream of water entering as a liquid at 8 megapascals and exiting as saturated vapor at 8 megapascals. So in other words, we're looking at the this is what's happening through the turbine on a TS diagram. This is 8 megapascals, right? So you have the stream of water entering as a liquid, and then it exits as a saturated vapor at 8 megapascals. Okay? So liquid at 8 megapascals and going out. Now, in a separate stream, gaseous products of combustion cool at a constant pressure of 1 atmosphere from 1107 to 547, because obviously the combustion creates hot gases, right, which run through the heat exchanger, right? So what's going to happen to the combustion gases? They're going to cool, right? Because their heat is being absorbed by the water. Okay? So in the process, you have water coming in like this, and heat is going, the air is going through here. This is at a normal, because the water is only pressurized within the pipes, right? And here is just at atmospheric pressure. The hot gases cool. The gaseous stream can be modeled as air at an ideal gas, okay, which is fine. And the dead temperature here is 22 degrees, the pressure is 1 atmosphere, so this is the dead state. The questions are, what is the net rate at which exergy is carried into the heat exchanger by the gas stream? Remember, this is an open system, right? So remember that EF in, EF out that we talked about when we did chapter 7, towards the end of chapter 7. So determine the net rate of heat exergy at which exergy is carried into the heat exchanger by the gas stream in megawatts, and the net rate at which exergy is carried from the heat exchanger by the water stream, okay? So it's pretty much the same equation in megawatts, and then the rate of exergy destruction, and then the exergetic efficiency, okay? So let's take a look at this. The engineering model is the heat exchanger. This looks like a counterflow heat exchanger, right? So the control volume that encloses this will show how many inlets. Well, I've got 2 inlets, right? 2 exits. The control volume in the accompanying figure operates at steady state with Q of the control volume and W of the control volume is 0. Okay. Kinetic potential is ignored. Okay, the dead state is about 1 atmosphere and 22 degrees. So let's figure this out. The analysis begins by evaluating the mass flow rates. Now, do you agree in here that the mass inlet, and this is the exit, right? And this is 1, no, this is 1 and 4. So the mass flow rate and the inlet and the exit has to be the same, right? And the same thing in here, m dot 1 and m dot 4 have to be the same because the two things do not mix, right? So steady state, the conservation of mass principle requires that m dot n equals m dot e for air, m4 and m1 are the same for water, right? Now, because this is an open system, the first law of thermodynamics applies, right? What does the first law of thermodynamics apply? Remember, dE over dt is 0 is equal to Q control volume minus W control volume plus m dot of the air. There's 2 fluids. M dot of the air, the change in minus exit, plus m dot of the water times H4 minus H1. That's just the first law of thermodynamics applied to the open system, okay? And we neglected, obviously, change in kinetic energy, change in potential energies here. In this equation, MA and M dot denote respectively the mass flow rates of air and water, which can be solved by M dot 8 H1 minus H4 is equal to H1 minus H4 divided by HI minus H exit. Can you tell me why? Where the heck does this equation come from? Well, let's look at the air, right? What is the heat? Well, the temperature has gone down, right? So what is the enthalpy change for the air? Or what is the enthalpy air for the enthalpy change for the air? or what is Q lost by air equal to? It's m dot air times the change in enthalpy of the air, which is what? What is the enthalpy higher? H1 or H in, right? Minus H exit. And then Q gained by water is equal to what? Same idea, right? M dot of water times what?
H1 minus H4.
H1 minus H4, right? Not H4 minus H1. I mean, the H1 is higher than H4, right? So these two better be equal because it's conservation. Whatever is lost from the hot gas has to equal to, so if you equate these two, you will get this, you see? M dot air times HI minus H exit is equal to M dot times H1 minus H4. So the solution to example 2 gives H1, so this, see, we have to refer to example 2, in which we got the H1, the H4, and then HI and HE, right? This is for air, that means you just look at the temperatures, you read, remember table 22, temperature is known, you can just read the values of H's immediately. So based on this, you can find what is the ratio of the mass of the air to the mass of the water. Now, what is the net rate at which exergy is carried into the heat exchanger? So what brings in exergy? It's obviously the air, the hot air, right? So we're gonna say it's the mass flow rate of the air times the flow exergy in minus the flow exergy at exit. Okay? And we know what the equation for this is, right? It's HI minus H exit plus minus T0 SI minus SE. So we calculate that. I don't want to go into the details of it, but that's what it is. And then you find it's 231.38, okay? The net exergy taken out of the boiler by the water, it's the same equation, M dot EF1 minus EF4. Same equation as before, right? And then you find in this case that it's 130.53, okay? So this is how much those hot gases, how much exergy they are bringing in, right? And this is how much the hot water is taking out, okay? So how come it's not taking out as much as is being brought in? Because there are losses. Remember, the value of that just gets lost as you go through, right? And it turns out that what's lost is really the difference between the two, okay? So the accounting, even though the energy is conserved, the value of the energy, which is signified by the exergy, gets lost, and it says the rate of exergy destruction by doing the exergy balance is simply equal to the difference between the two, okay? So the efficiency then is what? Remember, the efficiency is the exergy out taken by the hot fluid, by the water, divided by the exergy brought in by the hot gases, right? So if you take the ratio of the two, you find that the exergy is approximately 56.4%. And that concludes, I'm not going to do the other examples, but that concludes chapter 8, at least the important part of chapter 8. Whatever we talked about today is really kind of improvements to the cycle and this and that, but what you are supposed to know is what is behind a clean Rankine cycle, and how do you go about analyzing those. And now you got to be very clear though, the only problem with the Rankine cycle is what? Even though everything is based upon 4 enthalpies. Obviously, if you get the 4 enthalpies wrong, what happens? Yeah, that means even though the equations are all pretty clear, if you're plugging in all different numbers, that's not going to work. So anytime you do a Rankine cycle, most of your effort should be concentrated towards getting the actual values of the H's, you know? Don't rush, don't say it's just this, okay? Make sure you're getting the right values of H's, because the rest of the questions are pretty much, you're just plugging the values of H's, okay? So if you mess up the values of H, obviously it messes up everything else, okay? So let's take 5, and then we'll, give me time to bring up the, 9.
You were in this class.
I know that the homework is more involved before the exam.
Hmm?
This covers what we need to know about chapter 8 for the exam. Right?
Pretty much, you know? Yeah. Or you got this, you got that, at least for that, plus some auxiliary, you know, in that example, figuring out how to take out the heat from there, you know.
Right.
But that's an example anyway.
Right.
So I would say this and then look at that example, first example.
First example in the book.
Yeah. How to analyze an ideal Rankine cycle.
Trust us, we like it better that way.
No, it's not the example. Yeah. Yes.
Oh, okay.
Yeah.
Thanks.
You should be able to kind of reproduce that.
So, next week I will be on second shift, and the week after I'll be on second shift as well.
Okay.
So, yeah, I'm gonna talk to you about finding a time to take your test.
Okay, so
You said- yeah.
it's,
People usually pick their seats before.
so, when I'm here every day.
I've been doing it wrong.
Waiting till.
I'm here Monday, of course, Monday.
Actually,
I'll be here Tuesday.
last time I flew,
Usually Tuesday,
flight took off, so.
I'm here around 11:30, somewhere around there.
That'd be great. In fact, yeah, next Tuesday, maybe around 11:30 to noon.
Yeah.
Like, come over. Okay.
Yeah.
Oh, were you just saying cold here?
Yeah.
Now it's
Yeah.
cold here.
Would Wednesday also work? Or?
Wednesday, unfortunately, Wednesday, I'm gone until about
That's
He's really taking
12.
it out.
Okay.
Then I drive up here,
They have,
sometimes it takes
there
me
was
so long.
Gotcha. Okay, no worries.
Thursday,
And it's like-
Thursday.
Okay. Tuesday or Thursday?
Thursday, because I'm a TUW, so
Okay.
I finish at 10:45.
Then we'll just change to my one
So,
before.
I let it
right now.
Okay.
11:30, 12.
Okay.
somewhere around
Yeah.
there. So if we should plan by Tuesday,
Right.
Okay.
the day after these days.
Yeah.
Yeah.
Okay. Thank you very much. Sorry about that.
Okay.
Of all the things that
Erica
I
and
need,
Allison wants
Not a
to.
problem.
I think Allison still has one.
Okay, good.
I have a long
Pretty sure
one.
Erica will be okay with it.
I'm sure she'd be fine with it as well.
I got a question for you.
Uh-huh.
Last year
I'm
for-
noticing the homework. So, the second section, I don't know how they did it.
So
It's
you got like
really
the
different.
funny story or like the little ears. Then I got the little llama one and it has.
They have a different way of doing their head, so the solution manual instead of this one.
You weren't,
Uh,
so you didn't know.
What about you?
So they introduced another
Did
entropy,
3 months in
SFG.
I'm sorry.
Oh,
And so then I reached
because
out to
SFS, yeah.
Yeah.
Sometimes, yeah, I try not to use that one. Sometimes they have, for example, HFG is equals to HG minus HF.
Oh, is that right?
That's really what it is.
Oh, okay.
And SFG is the same thing as SG minus HF.
Oh, okay.
But I would probably stick with
Stick with this one.
this one. Like for example, I don't like them when they use this,
Oh,
right?
even other one.
Yeah, you see here? I would use perhaps H2 is equal to H1 plus X times HG minus HF. That's usually the way we write them.
Oh,
It's H, I guess, HF plus, one would say H is equal to HF plus X times HG minus HF. Some people call this HFG. So it's the same
It's the same thing.
It's
Gotcha.
exactly the same.
The same thing.
Yeah.
Gotcha.
Yeah. All right?
specifically conformities,
Oh.
but I'm almost done with my role there.
Look, whenever you do water, they're always gonna fail. You're gonna fail the process.
Does the phone get too much space because of the video?
Hey, what?
Your phone since the videos that you did?
Yeah.
Did I get?
Oh, yeah, yeah, actually, I'm trying to upload them to YouTube just so I can take them off my phone.
Oh, okay.
Yeah, I had I think last quarter I was recording one, and it just stopped recording because it was just out of space. It's like, dang.
You know, when we identify something as process, we can
Right.
record anything.
Technically.
Yeah, so, and they came out and said, yeah, you guys are right. This is a derivative, this is a new aircon, so that doesn't work. Yeah, he's over in the factory now by me, or kind of by me. DC and Dave and all those guys are still up there. So they're not gonna stop.
Smooth sailing, rolling over there. It's gonna be dead in a couple weeks.
Another blank number or
Yeah.
something.
Well, yeah, the schedule change. I don't know if you heard about the U64 schedule change. It's super slow. It's hard to say. We're obviously, you know, because it's like, we're green, right? The rest of that is bad. Of course, we're gonna slow down.
Yeah. I mean, it's good that all those people
Right.
are bringing in a whole bunch of manpower that just doesn't, when we don't even have the solid nominal baseline yet, bringing people that never even.
Yeah, done these,
Yeah,
schools and just add that to your place.
yeah,
I can't imagine going from a 3-7 to 777.
yeah.
All right.
I think a lot of those guys are good at that stuff. They work, right?
Oh,
And
yeah,
they do
they
their
work.
bar twice a day, and days fly by and they know what they're doing. I mean, here, I mean, anytime you should go out on the floor, you have to show the people working, just as many people walking around and, you know, in their pajamas looking at their cell phone.
Okay, let's keep going. So we finished 7, we finished 8. Now we're gonna get into 9 is a fairly long chapter, unfortunately, so we're gonna spend some 2 weeks or 2.5 weeks on it. It talks about, in the previous chapter, obviously, we talked about water being the working fluid, and the way you generate power is by changing the phase of the water from liquid to vapor or superheated vapor. You extract the heat, the process, you generate work through the turbine, and then you repeat the cycle. Now, not all power cycles, by definition, generate power, work with fluids. Some of them work with air or with just some, just through combustion. For example, let's go through this in here. Vapor power cycles or systems were studied in 8, use working fluids that are alternatively vaporized and condensed. So you alternate the vaporization and condensation. The objective of this chapter is to study power systems, again, vapor power systems, utilizing working products that are always a gas. So this is the key thing. No phase change in this case. Okay? When you talk about gases, there is no phase change. Included in these groups are gas turbines, internal combustion engines of the spark ignition type or the diesel type or the compression ignition type. We will conclude this chapter. There are 3 parts in this chapter, but we will conclude with a brief study of compressible flow in nozzles and diffusers, which are components of gas turbines for aircraft propulsion and other devices. Okay? So it's kind of a super rich thing. And you're going to learn many cycles in this chapter. In fact, at least 3 of them that you're going to be learning. In chapter 8, it was 1 cycle, which is the Rankine cycle. In this chapter, you're going to learn the Otto cycle, the diesel cycle, and the Brayton cycle. 3. Okay? So, in the first part, we will talk about IC engine, internal combustion engines, which you guys are, everybody's kind of more or less familiar with. We'll introduce the engine terminology, and then talk about the air standard Otto cycle. And then we'll go on with the diesel cycle, what is the difference between the two, and how we analyze them. We're gonna put them kind of in that same format as the vapor power cycle. In other words, you're gonna have a physical thing, and then a TS diagram of some sort. And then we will do what we call a dual cycle. A dual cycle, that means it uses part of the Otto cycle and part of the diesel cycle to kind of mimic a true engine performance. Then after we finish with internal combustion engines, not everything is internal combustion because everything is happening within a cylinder, right? You can have a gas turbine power plant, so which are kind of more of open systems. So modeling gas turbine power plants, how do you do that? And the cycle that talks about it is the air standard Brayton cycle. Now, for each of these cycles, obviously we're gonna go and talk about how do we improve efficiencies. So this is, again, the type of stuff that you do to improve the efficiency, but it increases the number of states that you have to evaluate. The first one is called the regenerative gas turbines, and the regenerative gas turbines with reheat and intercooling. So for the vapor power cycle, we're talking about the superheat and the reheat, okay? We're gonna be doing different things when we talk about gases now, okay? Different methods of improving the performance. And then we'll talk about gas turbines for aircraft propulsion, and then we'll talk about combined gas turbine, vapor power cycle, and then the Ericsson and the Stirling cycle. Then we'll move on through the last part, which talks about compressible flow preliminaries and analyzing 1D flow in nozzles and diffusers. And part of this, by the way, we will be also doing in the heat and fluids 2 course, We'll do a little bit of compressible flow at the end, okay? So what we don't catch here, we'll catch it then. Okay, so you can see that it's a lot of stuff. So let's start with the internal combustion engine. And it says, although most gas turbines are internal combustion engine, the name is usually applied to reciprocating, things that repeat, goes back and forth in combustion expansion. Internal combustion engines of the type commonly used in automobiles and trucks and buses, okay? So what we'll be concentrating on in this part is really cylinder with a piston, you know, and then you get a crankshaft and everything. How is the, remember the power is really is collected right at the crankshaft that is turning. You get a shaft that is turning there. And how is that work generated? Is obviously through the combustion of a air fuel mixture, right? Which is sparked, explosion occurs, you're pushing and getting the power, right? Which is pressure times force. You're pushing on the piston, which makes the shaft rotate, and then it's repeated through all, you know, in many cycles. So these engines differ from the power cycles because the process occurs within a reciprocating piston cylinder assembly. So all the action is occurring within this, you know? And then you go like, right, really, you know? But we'll have to make some assumptions. Why? Because in real life, in reality, it is not a closed system. Why? Because every cycle, what we are doing, you know, you got the inlet valve, right? After the exhaust valve, you open the inlet valve, you're pulling some fresh air, right? And then fuel mixture. And after the explosion or the combustion occurs, you know, you need to reject the stuff and then bring in a new charge, right? So you have constantly a change in the charge in the cylinder. But for purposes of analysis, we'll have to make assumptions that say, hey, everything is the same, right? We're not gonna worry about you exchanging and pulling in, so long as we make assumption A and assumption B, okay? So, and the other thing too, what is the difference between this and vapor power cycle? We know that for vapor power cycle, we have 4 open systems that are interconnected, right? This one, nothing. There's no turbine here, there's no condenser, there is no stuff. You just got one cylinder that's got stuff in it that gets recharged every cycle. So when we talk about the combustion engines, as we know, we have combustion engines of the spark ignition type or the compression ignition type. So this is a typical gasoline engine versus the typical diesel engine, right? So in the spark ignition, a mixture of air fuel is ignited by a spark plug. So you need to have a spark, you know, to create the combustion. Whereas in a compression ignition, you get spontaneous combustion just by virtue of the pressure, right? Because usually you're operating at higher pressure, so air is compressed to high enough pressure and temperature that combustion occurs spontaneously when fuel is injected. So, again, some just words in here about spark ignition engines. They have advantages for application requiring powers up to 220 kilowatts or 300 horsepower. They are usually light and low in cost, right? And they are particularly suited for use in automobiles. That's why most automobiles are of the spark ignition type. Compression ignition, on the other hand, are normally preferred for application when fuel economy and relatively large amounts of power are required. That's why you find them a lot in heavy trucks, buses, locomotives, ships, etc. What is the anatomy of a reciprocating piston cylinder engine, right? So obviously this is the cylinder, this is the piston, right? Spark plug or fuel injector, right? a combustion. You got 2 valves. There you got an inlet and exhaust valve. And this is the piston. This is the crank mechanism. And this crank, obviously this up and down motion, right, gets converted into a rotary motion, okay? So this is where the power is harvested, if you will, right? So some of the terms that are really important is when the piston is at this upper part right there, right? Obviously it does not get all the way here. There is a minimal volume that gets into there. We call this the top dead center, right? When it's all the way down, it is at the bottom dead center, okay? So and then the diameter of the cylinder is called the bore, and clearance volume is when you get to here, when it's at the top dead center. So the volume swept out by the piston as it moves from the top dead center, as the piston moves from this location down to this location, it's going to sweep what? What kind of volume? This volume, right? Which is equal to the cross-sectional area times the stroke, right? And we call that the displacement volume, okay? So as it moves from here to here, it's going to sweep a displacement volume. The compression ratio, because you are operating between two pressures, the compression ratio R is defined as the volume at the bottom dead center divided by the volume at the top dead center. Compression ratio R, okay? So if this volume is 8 times this volume, we call it compression ratio 8, et cetera, okay? The reciprocating motion, reciprocating up and down, of the piston is converted to a rotary motion. And how do you do that? It's obviously through a crank mechanism. Now, how many strokes does this internal combustion work with? Usually it's a 4-stroke engine, right? Because the piston executes 4 distinct strokes, right? For every 2 revolutions of this crankshaft. So each cycle is really what it is. Typically you've got, we'll talk about the 4 strokes in just a second. So, what is the first part? Is the intake stroke, okay? In the intake stroke, you have the intake valve open, right? So the piston makes an intake stroke to draw fresh air. So the piston is moving down, right? With the intake valve open. So what is it drawing? Obviously, it's drawing fresh air, right? So with the intake valve open, the piston makes an intake stroke to draw a fresh charge into the cylinder. So you get fuel plus air for spark plug ignition, or and only if it's a diesel one, okay? Okay, now the piston goes all the way down to the bottom dead center, right? The intake valve closes, right? Then what happens after that? You get the compression stroke. Now you need to take that charge and really compress it, increase its temperature and pressure. So with both valves closed, the piston undergoes a compression stroke, raising the temperature and pressure of the charge. Remember what happens to air when you compress it? That's what happens. You increase the pressure, increase the temperature. When the piston gets all the way near the top dead center, now the charge is really occupying the minimum volume, right? It's really compressed. Then what happens? It says when raising the temperature, a combustion process is then initiated near the end of the compression stroke, resulting in a high pressure, high temperature gas mixture. Now it's an exothermic reaction, so you're creating a high temperature, high pressure because of the combustion. So what happens to the piston? It gets pushed back down, right? That's the power stroke. That's where you're really pushing on the mechanism, you know, to create the work. That's the power stroke, whereby, see, now you're moving from the top dead center down to the bottom dead center. You're sweeping the entire volume, right? Because you're going to be pushed. At the end of the power stroke, it says whereby the gas mixture expands and work is done on the piston as it returns to the bottom dead center. Then what happens now? When the piston is down there, what's inside? It's just combustion gases, right? Combustion gases that are worthless to you. So what you do? The exhaust valve opens, right? The piston goes up and it rejects all those fumes, right? And then the exhaust valve closes, then the intake valve opens again, and you're repeating the same stuff, okay? Now, how many passes did the thing do? We're starting from the bottom, top dead center, fresh charge, bottom dead center, and then compression, okay? And then power stroke, and then exhaust, okay? So you did 2 passes, 4, and then you did 2 revolutions of the crankshaft, okay? Now, if you were to plot how the pressure would change as a function of the volume, you know, this is kind of what you get, some kind of weird thing. So here, obviously, you're operating between what volume and what volume? Well, the top dead center and the bottom dead center, right? What is state number one? State number one is when the intake, right here, the intake valve opens, so you're at the top dead center, intake, right? So the piston is moving down to the bottom dead center. Then what happens? The intake closes. Remember what comes after is the compression. You are compressing, you know, you get to about this top dead center, then what happens? Combustion is initiated. You are already at high pressure, but the combustion increases that pressure further up, right? And then you're coming down, and this is the power stroke. As you get to the bottom dead center, what happens? The exhaust valve opens, right? And then you continue on. Now you're exhausting all those fumes, and then you're coming back to the initial tank and go there. Now, this is not fun, right? Because the curve is not very clear. It's not something that is amenable to kind of nice little solutions, right? That's why we'll have to make approximations to kind of clean up this at some point. Okay, but a pressure versus volume, when you're talking about a gas, pressure versus volume is an important quantity. Why? Because if you remember, the integral of P dV, right, will tell you what the work is going to be. Okay, now you can have, not all engines are obviously four-stroke engines, you know, if you have a motorcycle or blower or whatever, right? Those are two-stroke engines, right? Or smaller engines operate on two-stroke cycles. I don't know if you guys have seen two-stroke engines, kind of how they operate. The piston does more work. It's got a lot of stuff, so but as it expands, you've got the valves are actually right there on the cylinder itself, right? So as the piston goes down, one valve opens and then the other one opens. So the exhaust and the inlet is not done separately, but they are kind of in conjunction with the, as the, what is it called? As the piston is moving, you know, they're done automatically. So that's why you can get two strokes with one revolution of the crankshaft. So although internal combustion engines undergo mechanical cycles, the cylinder contents do not execute the thermodynamic cycle. This is the big hick about this whole thing, okay? It's a cycle, but the working fluid is really not cycled, because every cycle I'm getting a fresh charge from outside, okay? So how are you gonna reconcile that? It says matter is introduced with one composition, and it's later discharged with another composition, you know, at a different composition at the end. So how is this all done? Now, because that pressure was kind of doing that weird looking thing, it says, thermodynamicists invented what they call the mean effective pressure, the MEP, okay? Instead of talking about something that does kind of like an 8 or something like that, it says a parameter used to describe the performance of a reciprocating piston engine is the mean effective pressure. And they go like, and I think I totally agree with them. It makes a lot of sense, because if you're going from one volume to another, that means that you're really, you know, you have a displacement volume, right? Do you agree that work is equal to the integral of P dV between V1 and V2? And then they said, hey, you know, we know how much the piston is moving, how much volume it is sweeping, right? So if we can assume that some average pressure exists, which I can consider to be constant, then I can say that this is probably something like P, right, times V2 minus V1, which is the displacement volume. Okay, so they said, okay, now I can say that this pressure, right, is simply equal, I'll call it the mean effective pressure, is simply equal to the work done in one cycle divided by V2 minus V1, which is the displacement volume. Okay? So, again, the mean effective pressure is the theoretical constant pressure. Theoretical constant, you can probably agree why we're saying theoretical constant, because it's changing. You know, it's doing all this stuff, but you can say, yeah, what is the average?
We call it constant for the math.
For the math, exactly, because the math, so long as the average between this cycle and this other cycle, this one is better, then this one will perform better than the other one, right? So it says the mean effective pressure in the theoretical constant pressure that, if it acted on the piston during the power cycle, would produce the same amount of work. Because if you can agree that if this is a constant pressure time the displacement volume, I can get the same amount of work. So it kind of makes sense that it is a good metric, if you will. So remember this one, MEP is equal to the net work done for one cycle divided by the displacement volume. Now, what is this useful for? Well, if you look at two engines that have the same displacement volume, right? The one that has a higher map, right, would produce what? The higher amount of work. It's as simple as that. You know, if V2 minus V1 is the same, right? If P is higher, you would get a higher work. Remember what the goal of this cycle is really to, it's a power cycle, so what is important is really the amount of work. So if the map would produce greater net work, and if the engines are at the same speeds, obviously greater power. Now, how are we gonna conduct an analysis on something that is really not truly a cycle, because we have one substance coming in and a different one, I mean, of one composition being ejected, exhausted, and another one of different composition that is brought in? It says to conduct elementary thermodynamic analyses of internal combustion engines, we call, again, this is a very important word in here, expression, which we call the air standard analysis. You'll hear about this a lot. Air standard analysis. What does it mean? Well, you're looking at this cylinder, right? Instead of saying that you have stuff going out and stuff coming in, we will assume that, hey, we have a fixed amount of air that is modeled as an ideal gas in the fluid. So we're not saying that we are bringing in new charge or we are exhausting an old charge. We're assuming that it's the same volume of air that is inside. Okay, cool. Number two, we know that there is a combustion because of the spark, right, and then the fuel air mixture and this and that. So we're not chemists, we're not gonna get into the combustion process or this or that. But what do we know about, what is that combustion process really doing? It's raising, it's creating that heat. Remember power cycle? Remember what a power cycle is, right? Q in, Q out, W cycle, which is equal to Q in minus Q out. Okay? So that combustion is really what's bringing in this Q in. Okay? So instead of talking about combustion, or getting dragged into how much air do I have or how much fuel or air, I just replace that combustion stuff with, I'm just gonna say, hey, the combustion process is replaced by a heat transfer from an external source. No details about production. We're just gonna say that when the piston is at the top dead center with that compressed air, I'm just adding heat. Okay? Cool. So combustion by a heat transfer from an external source. How about the exhaust? It says there is no exhaust, there are no exhaust or intake processes as in an actual engine. The cycle is completed by constant volume heat transfer process taking place while the piston is at the bottom dead center. Okay? So the cycle is completed by a constant volume heat transfer process. Remember at the end, what do? After combustion, after the power stroke, right? Instead of saying I'm gonna do a stroke in which I reject and then pull a new charge, we're just gonna say, hey, we're gonna be losing that heat. Because really what you are doing is that, you're exhausting or you're chasing away hot combustion products and getting a fresh, cooler air, right? That means really what you have done effectively is you have caused some heat transfer to occur. So at the combustion, so this one is really the combustion. And this one replaces what they call the exhaust, okay? Making these convenient approximations. And then we are also assuming what? All processes are internally reversible. In other words, there is no stray heat transfer, there is no stray stuff, etc. Okay? Now,
How accurate is it?
not very, but it gives you but it gives you kind of an idea when you do comparison between engines, if you will, you know, one versus the other. But it does not mimic the actual stuff. But that's the best we can do, you know. And there is another one, so you probably remember this. And then there is the cold air standard analysis. I want you to make kind of a difference between these two. This one, air standard analysis, this one has another word which is called cold air standard analysis. What is the difference between the two? Well, it says in addition, in a cold air standard analysis, the specific heats are assumed constant at their ambient temperature values. In other words, C sub P and C sub V are constant, which is going to be pretty helpful for some calculations, as you will see later on, okay? So, although an air standard analysis simplifies the study of IC engines considerably, values of the Mech and operating temperatures and pressures calculated on this basis may depart significantly from those of actual engines, okay? Accordingly, air standard analysis allows internal combustion engines to be examined only qualitatively. In other words, don't take this to mimic, and all the other stuff has to be done more experimentally than anything else. Still, insights concerning actual performance can result with such an approach.
So is that first statement, is it saying it's all of the qualities of the cold air standard plus the constant ambient temperature?
No.
Okay, so it's only just the one?
Yeah.
Okay.
So, in other words, when it says in addition in a cold air standard analysis, that means in addition to all these things in the previous, because this is what the air standard analysis is.
Okay.
You know,
Okay.
these are the approximations for there, and then we add the fact, when you add the fact that the CPs and CVs are constant, we call that cold air standard analysis. So it's just one more. Okay, now, move on to section number 2, in which we look at the air standard Otto cycle. Okay, this is our thing for this chapter, right? One of the first standards that we're going to be learning. The air standard Otto cycle is an ideal cycle. Remember, everything is assumed to be reversible and nice and everything. That assumes the heat addition occurs instantaneously while the piston is at the top dead center, and the cycle consists of 4 internally reversible processes in series. Okay, let's take a look at this. Remember what this represents. A,
Top dead center.
top dead center, bottom dead center, right? So between the bottom dead center and the top dead center, what is actually happening here? No, well, yes, it's compression, it's isentropic compression, right? Why is, because it's, everything is reversible, right? So here we're not saying that we have an intake or something like this, because your air is the same air that you're talking about. That means that the piston is at the bottom dead center. I have my amount of air, right? And then between 1 and 2, what happens? I'm compressing it isentropically. Then when I reach the top dead center, what's happening here? I'm adding heat. I'm not saying combustion, I'm just adding heat. Remember, that's the assumption. I'm adding heat. How? Is it constant volume, constant process, constant what? Constant volume. See, while the piston is right there at the top dead center, right? Instead of saying there is a combustion or this or that, we're just saying that some heat was added while the piston instantaneously, magically, right? Magically heat appears, right? At that point. At constant volume. You see, between 2 and 3. That's why, remember, isochoric means constant volume. Then what happens after that? Between 3 and 4. 3 and 4, you have that's the power stroke, right? So the piston is going from the top dead center to the bottom dead center. Now that's where you're generating the work. And how is that? Isentropically, because we assume that all processes are reversible. Then what happens here? The piston is where? At the bottom dead center. What's happening at the bottom dead center?
Heat magically leaves.
Heat magically leaves. Thank you. That's exactly how it is. Heat magically leaves. While the volume does not change, and it happens instantaneously, right? And then that same air that's in there now gets compressed again and does this and does that. Okay?
Just basically a big air spring.
Yeah, exactly. Right? So we have simplified the analysis as much as we could, right? But still we can get a pretty good insight. This is a PV diagram, pressure versus volume diagram. Why is it important to do a pressure volume diagram here, particularly when we're talking about air? Is because the area under the curve represents what? Work. Okay? So the enclosed area is the net work, but this is a TS diagram. Remember the TS diagram, the net area is a heat. Yeah, so work and heat. So again, for the TS diagram, obviously in state number 1, you know, no, this is the air standard photo cycle PS and TS diagram, yes. State number 1 is at the bottom dead center. See here, this, you know, at B, obviously the S is here. You go from 1 to 2 isentropically, right? That means we have to move up. 3 to 4 is isentropic. These are constant volume processes, okay? 4 internally reversible processes in series. So again, in words, 1 and 2 is an isentropic compression of the air as the piston moves from the bottom dead center to the top. 2 to 3 is a constant volume heat transfer to air from an external source. While the piston is at the top dead center, this process is intended to represent the ignition of the fuel-air mixture at the subsequent rapid burning. 3 to 4 is an isentropic expansion, which is the power stroke. And lastly, 4-1 is the constant volume heat rejected from the air while the piston is the bottom dead center, so that we could restart from that same beginning. Now, every time we talk about a power cycle, just like we did for a vapor power cycle, it's always a good idea to figure out what the heck is the efficiency, right? What is the efficiency in here? The efficiency, it says, is equal to U3 minus U2, and then minus U4 minus U1 divided by U3 minus U2. First of all, why are we using the internal energy in here? Because, let me ask the question. is our system in here for internal combustion engine, is this our system an open system or a closed system?
Modeling it as a closed system.
We are modeling it as a closed system, right? Remember, for open systems, we typically use the H's, right? But for closed system, we use the U's. You know, that's, remember the first law, Q minus W is equal to delta U, okay? Now, what is this U1? Let's go back to the previous cycle in here. Okay, so it says eta, remember what this is, what the eta is really the work divided by the heat in, right? W cycle, right? I guess that's W cycle. Divided by the heat in. That's the efficiency of any power cycle. Now let's take a look at this. Where the heck is the heat in occurring in here? Okay. Well, look at that, heat addition. Between which position and which position? 2 and 3, right? So it's obviously going to be U3 minus U2. That's why in the denominator here you have U3 minus U2. And what is this? What is the work? Well, the work cycle, isn't it true that it's equal to the Q cycle? Isn't it true that Q cycle is equal to W cycle for closed, you know, it's always the case. But what is Q cycle? Isn't that Q in minus Q out divided by Q in, right? So what is Q in, you think, in here? Well, Q in is U3 minus U2. What is Q out? U4 minus U1. You see, that's why you see U3 minus U2, which is Q in. This is Q out. And this is Q in. So the equation may kind of look odd, but it makes sense, right? If you go back to the basics. So the thermal efficiency is the ratio of the network of the cycle to the heat added, okay? So it so happens that this is what you get. So for the vapor power cycles, when we talk about those 4 states, you know, the typical values that we should be getting are the 4 H's, right? H1, H2, H3, H4. From there we get a lot of stuff. For an Otto cycle, you can probably get an idea. How many cycles are we, how many states are we really looking at? It's also 4 states.
4 U's.
But 4 U's, yes. So it's 4 U's instead of 4 H's, because the H's don't make sense in here. Well, just not yet. They will, but not at the moment. So which table are you going to be using in here? Just 22. You know, you don't have to be dancing between, you know, table A1 or A2 or superheated and then do this and do that, you know? Why? Because there is no phase change, right? It's air. You are making the assumption that it is air. Remember, air, to find the properties of air like enthalpy and this and that, what do you need to know?
Temperature.
Temperature, exactly, the temperature. So when air table data are used to conduct an analysis involving an air standard Otto cycle, the specific internal energy values required by above equation here can be obtained from table A22 or A22E, depending on which units, you know, you'll be using. Now, still in the cycle analysis, because for air, we will be talking about 2 isentropic processes, right? And we talked about this last term when we talked towards the end, I think, of chapter 6, if I recall, because that's where we were talking about entropy, and we talked about isentropic processes, and we were using the VR values, right? We will be looking at an example. I'm sure it's I'm gonna remember those again, right? So So we use what we call the relative volumes and the relative pressures. In this case, the relative volumes, as you go from one state to the other, right? And if it's a cold air standard analysis, you don't even have to do that. You can use this equation. Right? Because for cold air standard analysis, when C sub V is equal to a constant, and we determine these equations also in chapter 6, right? So T2 between two states, T2 and T1, because that's where the isentropic stuff is happening, or T4 and T3, the temperature changes are linked to the volume changes. And usually the volume changes are related to the compression ratio, which is typically given. So all those are easily calculated. Now, the cold air standard Otto cycle thermal efficiency is a function of the compression ratio, because you can see that in this previous equation. Well, of the compression ratio and K, and again, this is in general, this is for our knowledge, it is advantageous, obviously, to have higher compression ratio. We create more work, right? And better efficiency. So, in fact, if you were to plot the compression ratio and efficiency, this is what it does, right? So you can clearly see that as the compression ratio goes up, the efficiency also goes up. Now, this is, again, the important analysis. This is going to be in the second exam, you'll be expected to know how to analyze an Otto cycle. Okay? Which is kind of a
exam, not this one.
yeah, no. I think we'll keep it to the second. It's gonna come pretty soon, So, what do we have here? So for this operation, remember state 1 is when you have the it's like the beginning of the compression, right? Again, these numbers are really important, right? As opposed to the vapor power cycle, in which we talk about state 1 as being the entrance to the turbine. Here, state 1 is the beginning when the piston is down and you are compressing the air, right? So, and then 2 at the top dead center, then heat addition, right? Power cycle, and then heat rejection. So essentially, 4 different states. Let's take a look at this one, in which case you have a PV diagram that shows, so when you do problems like these, this is how you're supposed to kind of take a look at it. PV diagram, and there is obviously a TS diagram. Let's take a read. It says the temperature at the beginning of a compression process, which is essentially state number 1, okay, of an air standard. It did not say cold air standard, it just says an air standard, okay, cycle with a compression ratio of 8. When you hear a compression ratio, what do you need to write? Remember, a compression ratio is the volume at the bottom dead center divided by the volume at the top dead center, namely, it's V1. Remember, state number 1 is when you are at the bottom dead center. Make sense? It's the beginning of a compression ratio. That's where the volume is the largest. Divided by V2, which is equal to R, and it's equal to, in this case, it's 8, I believe. Yeah. With a compression ratio of 8 is 540. That means, again, I don't have T in here, but maybe in state number 1 I could say, the temperature here is 540 degrees. Right? Then what happens? It says, and the cylinder volume is 0.02. Okay, so you know what V2 is, right? Or V1 is, I should say. The maximum temperature during the cycle is 3600. So you're operating between this and then a maximum temperature of 3600 Rankine, okay? Which is right here. Okay? So this is always 1, 2, 3, and 4, going in this fashion. But on a TS diagram, the 1 always starts from here. You go from 1, 2, 3, kind of 4, like this. 1, 2, 3, 4. Okay? The 2 isentropic processes, and the 2, this is V is equal to constant, this is V is equal to constant. Okay? So this is obviously like that. Okay? So if this temperature is 540, this obviously has to be 3600. The maximum temperature during this is 36, and then you're asked to determine all 3 questions. The temperature and pressure at the end of each process. Usually that's the typical question that is asked. Okay? What is the pressure and temperature at the end of each process? In other words, what's P1, T1, what's P2, T2, what's P3, T3, what's P4, T4? Okay? Those 4. And then, what is the thermal efficiency? That means that for each one of those states, you have to find the U value, right? And then, what is the mean effective pressure? The mean effective pressure, once you find the work, right, you can figure out the rest. So, let's take a look at this one briefly here. Remember the engineering model. The analysis between 1 and 2, what kind of process is this? It's an isentropic process, isn't it? Okay? The first thing you need to do, first of all, which table do we need to look at is table 22E, because the units we are using are USCS units, right? So if I go back to my table on page 903, or something like that, right? You always start from state number 1. What's given by state number 1? Do you agree that the temperature is already known? 500, it's given. So what do we need to determine? We need to determine the pressure and the value of U. Okay? But it says the pressure and temperature, right? So we need to figure out something in there. It says the temperature at state number 1 is T1, right? So finding what U1 is, remember everything is a function of just the temperature. So if I go 540, I can read the value immediately as 9204 on page 903, okay? So, and that's exactly the same we're going to be doing all problems, okay? So you read, the value of U1 is done, okay? Now, because between 1 and 2 is an isentropic process, right? What you need to figure out is what is the VR. You see those columns that are in between the table, like columns 4 and 5? No, sorry, 5 and 6. What is the title on top of that? What does it say? Delta S equal to 0. Delta S equal to 0 means it's the isentropic. You only use that for isentropic processes. So, for that one, for 540 degrees, what is the value of VR? It's 144.32. Okay? So you just note that, okay? For state number 1 here, the value of VR is 144.32. And we know that VR2 over VR1 is equal to V2 divided by V1. Okay? VR2 divided by VR1 is equal to V2 minus V2 over V1. V2 over V1 we already know. VR1 we read it from the table, that means we can calculate VR2. When we calculate VR2 we find 18.04. Then what do we do with it? We're still on that same table. We try to look for a value where that VR is equal to 18.04. So I look at page 903, I don't see anything there. Or maybe I do. No, on the right-hand side, remember, by the way, big issue here that students have had problems with. That table actually should have kind of a thick line in the middle, because it's the right-hand side is a continuation of the left-hand side, okay? So I always ask the students to make a note of that or to throw it, because you don't want to, you see, the temperature ends at 920, then it picks up at 940 on the top right. Okay, don't say I didn't tell you, you know? Because then I keep looking, what is VR? VR on the top right starts at 3541. I keep going down and I'm searching for what? For 1804, right? 1804 is where? Well, it's between 1200 and 1240. To find the exact, you have to do interpolation, okay? So if you do the interpolation, you will get 1212. Okay? You see, for isentropic processes, it's the VR values that you use to figure out what is the end state. See, we did not move from this table, everything is there. So you calculate VR2 over VR1 is the same thing as V2 over V1. Once you find this, we find what that next state is, and by the same time, by the same token, what is my value of U2 going to be? Well, it's going to be between what? Between 208.05, 209.05, and 216.53. Which one? It's going to be interpolated likewise, right? And you should be getting something like 211.3. You see, now you got state 1 with the temperature known, right? U1 known. Before we move on to state number 2, we figured out, first of all, what the temperature of state number 2 was, because it was not given to us. It's 1212, right? Now, what am I lacking? I'm lacking, what is my P2, okay? Because P1 is obviously 1 atmosphere, right? And it's an ideal gas. What is an ideal gas? PV is equal to RT, right? But P1 V1 equals RT1, and therefore P2 V2 is equal to RT2, right? So, but the V's are between 1 and 2. Is the V changing? No. So if I take the ratio of these two, I get P1 over P2 is equal to T1 over, oh, no, sorry, I made a mistake. That's what I meant to say, is that P1, PV over T is equal to a constant, right? That's another way of writing the ideal gas equation, right? So you can say that P1 V1 over T1 is equal to P2 V2 over T2. And from there, you can say that P2 is equal to P1 times T2 over T1 times V1 over V2. That's always the way you will be doing that. See, it's P1 T2 over V1 times V1 over V2. Now, the temperature at T2 is known, the temperature at T1 is known, V1 over V2 is known, right? It's the compression ratio. So it's immediately you find what is 2. You're starting from 1 atmosphere, and after you compress, you actually have reached 19 atmospheres, or 17, 18 atmospheres approximately. Okay? And then you march from there to there. Like between, are we okay now between 1 and 2? I think we're good, right? Now between 2 and 3, the process is not isentropic, it is constant volume, okay? So what happens, right? Since process 2 to 3 occurs at constant volume, when you have PV over T is equal to a constant, right? So V2 minus V1 becomes 1. So the following P would be the previous P divided by the temperature ratios. See? P3 is equal to P2 times T3 over T2, which happens to be 53.3. And then the temperature at T3 is given because that's the maximum temperature of the cycle. So for that, no big deal. I can read directly from the table at 3600, if such thing exists. I think onto the next page. On page 904 at 3600, I see a value of U of 721.44. Oh, there it is, 721.44. Okay, and because 3 is the beginning of an isentropic process, what should I be reading? The VR value. Okay, what is the value of VR at 3600? It's it's 0.6449. See, 0.6449. What do I need to do now between 3 and 4? I need to find the value of VR4. How is that? Well, VR4 divided by VR3 is equal to V4 divided by V3. Now, do we know what V4 divided by V3 is? You know, remember, 4 to 3 is the same thing as V1 over V2. V4 over V3 is the same thing as V1 over V2. Okay? When you draw the system like this. Okay? So V4 minus V3 over V3 is the same thing as V1 over V2. Now you find 5.16. Then what do you do after you compute the VR? You try to locate it on the table. See? And I look on page 904, it's not there, right? Because the maximum value of VR there is what? 3.176. So I probably need to go to the previous page. And 5.16 will be between what and what? Which temperature and which temperature? 1850 or 1900, yes. Okay, so you have to do an interpolation, and it happens to be 1878, and the same idea. So it's the same repeating, boring stuff that you'll be doing, you know. You find a U4, and then finding what the pressure is again, because it's the same volume, right? P4 over P1 is the same thing as T4 over T1. Now, by the time you reach this point, for those 4 states, you know what? You know the pressure, the temperature, and the internal energy. That's what an Otto cycle is all about. For each one of those states, you have the U values, you have the T values, you have the P values. Then after that, you know, after you get those properties, the rest of it is a walk in the park, right? You know, thermal efficiency, you just pick up the equation for thermal efficiency, you put in the stuff, you find, oh, thermal efficiency is 51%. And then you go like, what is the mean effective pressure? Well, the mean effective pressure is really the work of the cycle divided by that volume change, okay? So W is equal to MU3 minus U4 minus U3 minus U2, except because this is work per unit mass. Did we know how much mass we had inside the cylinder to start with? But we know what was the initial temperature, we know the initial pressure, right? And we know the initial volume. Is that enough with a gas, thing to kind of figure out mass? I think so. Why? Because you have PV is equal to MRT, right? So you do that, you find what the mass is, and then finding what the work of the cycle, and then the displacement volume, and then find what is the average pressure, which is called the MEP. Remember, it started for 1 atmosphere, went up to about 18, I believe, right? But really the Mech in this particular case has a value of approximately 8.43. Okay. Yeah, I don't think I need to get to the diesel cycle yet. It's a little too much. You guys can you guys stay another 15 minutes maybe? Or have you had enough?
We're gonna go over what's gonna be on the midterm and all that, or?
Well, the midterm is, let's talk about the midterm. The midterm is only going to cover chapter 7 and 8, right? We're probably going to have 2 questions at most, maybe 1 question from chapter 7, 1 question from chapter 8. In chapter 8, it's pretty darn clear. You need to be able to analyze a vapor power cycle, the ranking, just like it's in the book, okay? So normally you should have it as closed book so you don't follow, but you know, I'm gonna have it open book so you can, so it's gonna be open book,
It's open note.
open note, right?
How many?
2 questions?
How many damn turbines are gonna be in there?
No, just one simple cycle. I mean, I'm gonna really make it simple, really.
Yeah.
2
You know?
questions for the whole exam, you said that? 2 or
Well,
3?
1 question from chapter 7, 1 question from chapter 8. That's what I'm thinking at the moment, okay?
So 2 questions.
Yeah, 2 problems, you know. Well, the reason I'm doing that is because those cycles, you know, they may look easy, but the problem is they are lengthy.
Yeah.
So, you know, try to test yourself. I mean, as good preparation for this exam, take that vapor power cycle that's on chapter 8, problem example number 1, right? And first example in the book, right? How to analyze an ideal Rankine cycle, and try to do it without looking. You know, if you can reproduce that, you should not have any problem at all, okay? And then for chapter 7, it's going to be some, we had only about 2 or 3 equations, right? How do you find the exergy of a state when the dead state is given? So remember U minus U naught, E minus that. Or how does an exergy state changes from 1 to 2? Just look at the homework on that one, right? One thing you need to remember, not being too specific in here.
That's okay.
Yeah.
When you are given a rigid container, what's the thing that pops in
Volume
your head?
doesn't change.
Okay, that's all I need to say. I've said more than I should have said. So remember, next week we're not going to be doing the exam right away. Remember the usual way, we do it 1 hour of stuff and then we do the exam, okay? Yeah.
Are these gonna be pretty straightforward, or are they gonna be, or say you give us the output of a turbine and some sort of efficiency,
No,
we gotta work back into
it's not gonna, it's not gonna be convoluted. It's
Okay.
going to be like the
Okay.
I'm not, you know, like the example. I mean, I'm being really generous this time. Well, open book, and you know, I can do better. But because it is generous like that, I'm gonna be more. All righty?